So we can have wave pulses, and the key behind a wave pulse, or the key concept here, is that wave phenomena travel through the medium, but the medium itself doesn't necessarily move. So I can send big fat pulses down here. Let's see. Have fun. There we go. Let's send a bigger pulse. There we go. Right. Okay. And basically the notion is that I can send a disturbance through the medium, but the medium itself doesn't go down and back, right? The medium is just transmitting the pulse, right? That's the key concept, right? And in this case, this is actually called a transverse wave or transverse pulse. And that's because the thing is going that way, and the motion of the pulse is actually up and down like this, right? It's like that. And there are other types of pulses that I can send on this, and I'll show you some of those later. Okay. And so the wave, we talk about a wave speed. The wave speed is in the direction the disturbance is moving, and the velocity of the rope or the particle is more or less across this. This is like a continual wave. Let's see if I can make a continual wave on here. It's like traveling by, right? Eventually they like reflect and then get so messy that it's really not very easy to see. But that's the notion, right? Is we could have like an ocean wave or something like that traveling by like this. Where is it? Is it working in Chrome? I think it was. There it is. It's like subtly will hypnotize you. You'd be like, I will vote for liberal candidates. All of my years as an active voter. There we have it. Anyway, there's no subliminal messages like that. We'll go back to our thing there. Right? Okay. Okay, and here's the important principle number one. It's so important that it scrolls in slowly from the left side, right? The waves move through the medium just goes back and forth. And there's different ways that it can go. Like sound, for example, sound is weird. If I make a sound like this, the air is actually moving this way. This is called a longitudinal wave. You just saw a transverse wave. Ocean waves are transverse. But the notion is that once the sound goes by, the medium is pretty much back where it started, right? That's important principle one. And then what's the other important principle? There's two important principles. Aren't you curious what the other one is? The other important principle besides Mr. Bernard. Oh, that's a terrible sine wave. Look at that. I started out really good. And it's like, what happened? That's important principle number one, right? And then we've got sort of the anatomy of a wave, right? This thing here is just like in simple harmonic motion, the amplitude. Right, so for an ocean wave, they talk about the height of the wave. And it's not measured, I mean, I don't know for sure about ocean waves, but in physics, we don't measure from crest to trough. It's the disturbance from equilibrium that it is, right? So there's imagine the ocean surface as smooth, and a wave travels through, and it's how much higher than that smooth surface the peak is, or how much lower the trough is, right? And then, to some, that's a surprise that you spell trough that way, right? God help you if you're trying to learn English, right? Okay, and then a wavelength is from crest to crest. This is a wavelength, and it's the backward Y thing like that, right? That's lambda, the Greek letter lambda. Lambda. Lambda? Is that how you spell lambda? Seems like it is. It looks wrong to me now, though. It's got a B and a D, though. Lambda. There it is. You could measure it equally from here to here, right? That's also lambda. Okay? Just be very careful. This is not lambda. That is not lambda. That is half of lambda. Yeah, we'll get to this later when we look at waves. Right? That's half of it. This is the whole lambda, right? So it's easiest to go crest to crest. That's the easiest thing to describe. If you say from the middle to the middle, then you got to say from the middle going up to the middle going up, because you pass it somewhere in the middle, right? Okay. And of course, these things move with a characteristic velocity, a wave speed. Okay. So, yeah. So the medium is the material through which the wave travels. Amplitude is how big or how bright or how loud something is, right? The wavelength, lambda, there it is in meters. And lambda literally means the length of the wave, hence the term wavelength, huh? Yeah, if you'd known you'd had to think so hard today, right? Now let's do there's two things. There's two other things, right? Period now is the time for a wave to pass. And F is the waves per second that pass, right? So this is the period, right? This is the frequency, right? And this is the waves per second, right? Yeah? So there's all sorts of things that we could do, but let's just head this play, right? Let's suppose that our frequency is 4 waves a second go by us. Let's suppose every wave is 5 meters long. 4 waves a second, each of them 5 meters long, go by you. How fast are these waves going? 4 waves a second, each of them 5 meters long, go by you. It's like, think of railroad cars. How fast is that train going? Is it going 20 meters per second? Yeah, let's try another one. Let's suppose 10 are going by every second. 10 rail cars go by, each one 30 meters long. How fast is that train going? Wow, it's going really fast. It's almost going the speed of sound. It's going 300 meters per second, right? We don't have that train yet, right? Okay. So what we're talking about here, there's a relationship, and that this is the most important thing in the entire chapter, is that velocity is the frequency times the wavelength, and that's in the data packet. Okay. So if you have a frequency of, say, 100 hertz, right? That's kind of a low note. 100 hertz, and each wave is half a meter long. How fast is the wave going? Yeah, 50 meters per second, right? We can do that, right? Or if we have an organ pipe that has, it's putting out a frequency of 440 hertz, right? Frequency is that, and the speed of sound is 343 meters per second, right? The organ pipe, if it's going to fit a whole wavelength, and they don't have to fit a whole wavelength, very few do, most fit like a half or a quarter, has to do with geometry, right? But a whole wavelength is what? Well, it's going to be this 343 that it goes in 1 second divided into 440 parts. So you should be able to solve these kind of with your, I don't know, don't dinosaurs have like 2 brains? Like they thought they had like a brain in their butt? To like, seriously, there was this theory, I don't know if it's a current theory, but they thought maybe like a big brontosaurus or apatosaurus would have a brain in its butt. To like, because there'd be such a lag time between the front of the dinosaur and the back. They thought maybe they had like a auxiliary brain or something like that, right? Yeah? Okay, so I'm thinking you ought to be able to solve these things with that butt brain that you have, right? I'm not calling you a butt brain. I'm just saying if you had an auxiliary brain, you could train it to solve these things, right? So the notion is, how far does it go? In 1 second it goes 343 meters, and that's divided into 440 equal parts, right? So see if you can solve this one. 0.7795 meters, yeah? Let's hit the right arrow, see if there's anything else. Wave speed, period. You can also make your own formula. If the wave length is the length of the wave and t is the time for it to pass, isn't the velocity also lambda over t? Not in your data packet, but that's handy, isn't it? That's also true, isn't it? If it goes 20 meters in 0.2 seconds, it's going 100 meters per second, right? Isn't it? That one's not in your data packet, though. hit the right arrow.